Hello grade 10s, welcome to yet another video, and today we're going to be reviewing this paper that was written in the term 1 exams from the KZN. Again, I'm doing this because of the availability of these papers. Otherwise I could have chosen any other province, so depending on how many I can find, that will be as many as I will do. Okay, so if you're new to this channel, welcome, and I can suggest that you may want to subscribe to the channel, because every now and then we'll keep on doing reviews before your exams. But this one is already an exam that has been written, so it helps you to prepare for your final exams at least. But we will do a review of a paper that may prepare you for your next exam. Okay, so if you look at this paper and you look at the paper I have done before you wrote these exams, you will see why it is so important to pay attention to these reviews. Okay, so let's go for it. So this is a 1.5 hour paper for 75 marks. I've already highlighted exactly what is necessary just to save time. So you know that you need to leave a line between two sub-questions and essentially make sure you show all formulae and substitutions in all calculations. Why? Because this is most likely the area where you can pick up most of the marks. Okay, round off your final numerical answers to a minimum of 2 decimal places, meaning no less than 2 decimal places is acceptable for this paper. Okay, give brief motivations, discussions, etc. where required, and then of course write neatly and legibly. Okay, now that we've paid attention to some general instructions, there is local instructions, so please read these ones. Each question has its specific local instruction which takes precedence over the general instructions. So make sure you don't mess up when it comes to this. Now 1.1 says the maximum displacement of a particle from its rest position is known as its, now we're talking waves. So let's say we have our rest position right here, and then we've got our wave. Let's pick another color. We've got our wave doing stuff like that, like a proper sine wave. And we know that the maximum displacement from rest position is what gives us an amplitude. So meaning you just need to know certain parameters of a wave. Okay, so don't mess up because it's not necessary. So basically the maximum displacement, just remember that it has to be a maximum displacement. It is the amplitude. Okay, so that's what it is. All right, now which one of the following statements is true? Okay, I don't want to talk about the others, wavelength and frequency and period. You need to know what they are. Okay. So basically a wavelength is the distance between two successive points, okay, in a wave. All right, that is what is a wavelength. So it's the distance between two successive points in phase, by the way. Those points have to be in phase, all right, to give us a wavelength. And then the frequency basically is, what can we say, is the number of waves passing a point or a given point in 1 second, right? Right. So it's not necessarily just the time it takes for a particular wave, but it's a number of waves that pass a given point in 1 second. Then the period is the time that it takes to complete a full wave, all right? So that is why those are not the answers. Okay, please know these definitions, they are important. Now, which one of the following statements is true? Sound waves can travel in a vacuum. Well, we don't think so. No. The answer is a definite no. Sound waves are electromagnetic waves. No, they are not. Remember, what are the electromagnetic waves? If you're coming from the lowest frequency, or should we say the longest wavelength, to the shortest or highest frequency, we're talking about radio waves, okay? Going into microwaves, going into infrared waves, going into visible light, okay, spectrum. And then we're talking about ultraviolet, we're going to X-rays and gamma rays. So those are the electromagnetic waves, and they have nothing to do with sound waves, because you almost don't hear a sound when we're talking about those waves, okay? Now the speed of sound waves is always constant, not necessarily always. It depends on the medium in which it travels, okay? So the answer is a definite no. The pitch, now that is the sound quality. Pitch is basically the quality of sound. Okay, is dependent on its frequency, and that is true. So that is the statement we're looking for. All right, so please guys be able to understand what is going on. An interesting question is why sound waves are unable to travel in a vacuum. Just find that out for me. It's quite an interesting one. Of course, I'll give you an answer in the comment section a little bit later on if you have interacted, but if you have not, then it means you're not interested. Then I will not give an answer myself. All right, let's look on to question 1.3. The diagrams below represent two sound waves A and B. Okay, so what is noticeable about the sound waves? Let's just first check how long does it take to complete a full wave. So this is a small block, right? It completes a full wave here on this block, isn't it? Because a full wave is from the beginning like that, okay? So it's from that block to this small block right there. So that is a full wave. And then let's analyze this one. Okay, so what is the story here? We're starting from this small block. We don't really know the units here, but if we were to know, we would be able to calculate at least the time that is, if that be time. If it is not time, then it's another story. But at this point, the horizontal axis usually on these graphs gives us time. Okay, that's what you understand from waves. Now let's see, okay, how long does it take to complete a wave? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we're getting 20, time units, which we don't know what that is, but we can assume this is seconds. Now let's see about this one. So we can see that the period here, if we assume that this is seconds, this is 20 seconds. We're just assuming it's a second. Nobody told us anything about the unit of measurement of the horizontal axis. But this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So the same story happens here. If we assume the small block represents a second, so the period is the same. Okay. All right. Okay. So we can almost tell that, okay, these ones, if, for example, the period of B is equal to the period of A, what does that mean? We can make a conclusion that the frequency of B is definitely the same as the frequency of A. So meaning these two sounds will be of the same quality. Okay, so that is the conclusion we can make from noticing that the periods are essentially the same. Okay, but how do we know this? We know that frequency is inversely proportional to the period. In fact, the equation is saying frequency is basically 1 over period. So we can tell that if we were to calculate the frequency for each, we would essentially come to the same value. But there is something strange here. What is the strange thing? If we look at, coming from the bottom, from rest position to, the maximum displacement, we can see that these two waves are not the same, right? Of course, if we assume that the small block represents a meter, you would know that for A, we've got 1, 2, 3, 4, 5, 6, 7, 8 meters, whereas this one is 1, 2, 3, 4. So it's half of the other. So the amplitudes are different. So if we say, for example, I'll just use A for amplitude of B is less than the amplitude of A. Okay, don't know why my A wants to look like that. Okay, now what do we know about amplitudes? Amplitudes are related to loudness. This implies that the sound A what is this now? It's starting to irritate me. Sound of A is louder than sound B, because B has a smaller amplitude than that of A. Okay, so basically these are some of the things you want to cement in your mind. So be able to analyze information that is given to you and be familiar with using graphs and any diagrams that are provided to you. There's something here, I don't know, it's really trying to irritate me. Anyway, so this is just a small analysis. Always whenever you're given something, be in a position to analyze and try to make sense of all the information provided. Okay, now the question says, which one of the following combinations that compares the frequency and the loudness of A with B is correct? Okay, frequency of A, we can see the frequency is the same because they have the same period to complete one full wave. So we know that the frequency should be the same. So all the options that are already saying otherwise, it's already wrong. Then now let's talk about loudness. Loudness is related to amplitude, not frequency, okay? Frequency is sound quality, but the loudness is related to amplitude. So we can already tell that A's loudness is greater than that of B because of its greater amplitude. So anything otherwise is not correct. So which one ticks all the boxes is D. That's the answer we're looking for. All right, great. Let's move on. Next question says, which one of the following statements best describes the behavior of an electromagnetic wave? So what do you know about electromagnetic waves? Well, electromagnetic waves, they're basically some form of radiation, okay? So radiation, if we're starting from the smallest to the greatest. Remember, you've got 7 types of electromagnetic waves that you need to know. You know that we've got radio waves. I'll just read radio. Then the next ones, we're starting from the smallest to the, when I say smallest, let's just say to the less energy to the highest energy, or should we say less frequency to the highest frequency, since frequency is related to the energy of a particular wave. So it's going to be radio going to microwaves. Okay? Going to, now you know that this is infrared. I don't know why it's blinking. Infrared going into, this is visible light spectrum. Visible spectrum, let's just say spectrum or light spectrum. Maybe let's write visible light here. Let's just say visible light or visible light spectrum. And then from here we're going to ultraviolet. Let's just say UV. Okay? From ultraviolet we get X-rays. Okay? And then we get gamma rays. Okay. Now, let's just leave it at that. So these are some of the things that you need to be able to appreciate. Okay, something is just not right here. I don't like how this came out. So this is basically gamma rays. Yeah, doch. This thing is throwing my time, and I think I'm gonna be angry with it. Gamma rays, okay, not a problem. So please know them. This is low frequency, this is low frequency, this is the highest frequency, and we are doing them in increasing order of their frequency or decreasing order of their wavelengths. Okay, not a problem. So now what do we know? The electric and magnetic fields vibrate perpendicularly to one another. That is true. That is one thing you need to know, because it does have an electric field because there's electrons, isn't it? And then there is also a magnetic field, because we know that anything that has a current will have a magnetic field as well as an electric field around it. Okay, that's interesting, but that is true. So if we wanted the statement that best describes that behavior, we already have found it. All right, so that is the answer already. So the electric and magnetic field vibrate parallel. No, it's not parallel, but perpendicular. The electric field is vibrating and the magnetic field is stationary. Not true. They are both vibrating. There's no stationary one. So the issue here is that there's no stationary fields there. They are vibrating, and that's it. Okay, great. So that is why A is the answer. So please know something about electromagnetic waves. Please, please, please. It's not really a difficult one. Just read something about it, know these particular waves, and at least be able to identify these if you're given a diagram. All right. Now let's do 1.5. It says now Elena has determined the charges on various objects. Which value has been incorrectly calculated? How would you know? Well, we know that the incorrect number here is not a multiple of 1,6 times 10 to the exponent minus 19 coulombs, which is a charge on an electron. So if it is not a multiple, it means it won't be able to divide. It won't be able to divide our charge on an electron into a whole number. That's what is important. So let's take this one and divide by 1,6 times 10 to the minus 19 coulombs. And let's see, of course the coulombs will cancel. So it's 9,6 times 10 to the minus 19 divided by 1,6 times 10 to the minus 19. So we're getting 6. So because this is a whole number, this means this number is a multiple of this. Therefore, it's not the correct answer because we don't want the correct value. Now let's do the same here. Coulombs will cancel, so 6.4 times 10 to the minus 19 divided by 1,6 times 10 to the minus 19. It gives us a 4. Again, we're getting a whole number. If that's the case, if we're getting a whole number, then it is not the correct answer because we don't want the correct value, okay? So let's do 4,8 times 10 to the minus 19 divided by 1,6 times 10 to the minus 19. Nope, something is not right. 4,8 times 10 to the minus 19 divided by 1,6 times 10 to the minus 19. So if we do this, coulombs will cancel, and then I'm getting a whole number 3. So that we don't want because we want the incorrect value. Most likely this one is the value, right? Okay, let's demonstrate that. So we've got 4,0 times 10 to the exponent minus 19 divided by 1,6 times 10 to the exponent to the exponent minus 19. So here I'm getting a 2,5. So do you see we're getting a decimal? So that means it's the correct answer because we can't have half electrons in a particular charge because we assume electrons to be a whole number, so to speak. So we can't have a 2.5. All right. So that means this is the one that is probably not correctly calculated. Okay, so that's cool. Let's move on. Now the voltmeter the voltmeter below reads 8 volts. Okay, now what is the story? We can see here conventional current. Remember these long ones always depict the positive terminal, and then the shorter ones always depict the negative terminal of our battery. All right, remember that. And conventional current is presumed to travel from the positive terminal to the negative terminal. But what is the flow of electrons? Electrons, however, I know that this is going to cause trouble. They flow in the opposite direction. Okay. All right. Okay, so let's leave that for now. Let's just accept the conventional current as it is. So this will flow. So you can see that these resistors are in series with the battery. Okay, so meaning the total current is what passes through both. And we are told here that this is 8 volts. V is equal to 8, or do I really need to? So if it is 8 volts, that means we can find the total current passing through these two resistors. Not a problem. Now the question says the EMF of the battery is, now EMF, which is the electromotive force, or the force that moves a charge across a circuit, is what? Now in our diagram we don't see any indication of the so-called internal resistance, and by the way, for your level you don't talk of internal resistance, so we're talking about the terminal voltage, right, which is the voltage across the terminals of the battery when the current is passing through the circuit. That we assume to be the EMF. So what we want is the total. Now how do we start? We need the total current, so we know that V equals IR according to Ohm's law. Then we want I tot is going to be V over R. So if we use the 10 ohm resistance, because we have a lot of info about it, it is the voltage across it divided by the resistance. Now 10 to 8 goes 0 times, you put a 0 there. 10 to 8 it goes 80 times, so this is 0.8 amperes. Okay, so we know the current passing through this circuit is 0.8 amperes. How do we use this? Then we will know that our EMF is going to be the voltage across the 10 ohm resistor, which is 8, plus the voltage across the 5 ohm resistor, which is going to be IR, isn't it, which is going to be 0.8 into 5. So let's do the calculation over there. So it's going to be 8 plus 0.8 into 5. So I'm getting 12 volts. Of course, if you were doing grade 12, you would know that this is the total external voltage. But because we probably assumed that the internal resistance of this battery is negligible, it means the EMF is essentially equal to the terminal voltage. So that is the story. So again, these are some of the questions you cannot answer without some form of a calculation. You cannot guess the answer, and there's no sense in trying to explain other answers here because they were not at all candidates. Great stuff, not a problem. So this is how you could get those 12 marks. Okay, let's just move on, guys. I don't want to take forever. So question 2 says the diagram below shows two pulses P and Q traveling in opposite directions in the same medium. Okay, now pulse Q travels to the left. All right, so you can see here they've shown us the direction of travel, and if this is traveling to the left, it means pulse P is traveling to the right. Okay, that's what it means. Now let's look. The amplitude of pulse P is 3 centimeters, okay, and that of pulse Q is unknown. Potential question. The two pulses meet at point X, and the resulting amplitude is shown below. Okay, so there's our amplitude. It is 5 centimeters in the negative direction. Now we have to decide, because we have an up and down, so we can choose that up is positive and to the right is positive as well. Okay, so you can decide here. Up, how do I write this? Let's just leave this one because we're going to deal with these ones. So we can choose up as positive or to the right as in the positive direction. Okay, so it is 5. So we know that these two are in opposite directions. When they are right here, the resultant pulse here is going to be the difference of the two. Obviously. And we can see that this is essentially on the baseline. So it's in rest position. No, I'm lying. It's not, because now remember at X, this is what we're getting. So we're going into the negative direction, basically. So we can see that the resultant pulse here is actually in the opposite direction to the initial. So What do we do then? Well, let's see what are the questions that we're being hit with and see what we can do about it. Now define the word, not world-ish. You know this English. Okay, let's define what a pulse is. So basically, we know that a pulse is essentially defined as a single disturbance that moves in a medium. Okay, so we can say a pulse is defined as in fact it's basically any single disturbance that moves in a medium. Okay, so that is the definition. Of course, you can read multiple books and all of that, exam guidelines, you name them. If you don't destroy the science, you should not be in trouble. You don't have to cram a definition from a single particular document. If you want to do that, rather do that on your exam guidelines because they help you more than the rest. Others may make it a little bit more complicated. Others can make it a little bit more simpler. At the end of the day, you just make sure the science is maintained in any definition, even if it is phrased in your own words. You don't have to be a copycat. You need to demonstrate that you actually have an understanding. We were challenged to always define things, or at least to express certain arguments in our own words, of course maintaining the science. And I thought that was the most important part of the so-called education. To just cram and regurgitate actually narrows your thinking, it narrows your imagination, it narrows your functional capacity of your brain. So do you really want to be that static? I don't think so. Anyway, you decide what is risky and safe. For me, taking risks is what makes you grow. But playing safe all the time makes you useless, even when we expect the most from you. Now, let's not talk about that too much. We are discussing physical science. So what type of interference takes place at X? Remember, this did not result into these two adding up nicely into a positive value. You can see that whatever this is and that, remember that was positive and negative, so these ones destroy each other, or they cancel each other to some extent. So this is what we call interference, isn't it? When two waves are traveling in opposite directions and they meet at a particular point, there's what we call interference. Now there's two forms: constructive when they're in the same direction, meaning they'll result into a bigger wave or a bigger amplitude, which would be the additions of those two together in the same direction. But when they are perhaps of equal magnitudes but in different directions, then they will take each other into a zero, and that's what we call a destructive interference. Since here we did a subtraction because they're in different directions, it is essentially what is called a destructive interference. Okay, so please be familiar with these kinds of terms, okay, as to what is actually the so-called interference, and then what do we mean by constructive versus destructive interference. Okay, so there's some keywords to really mind here. 2.3 says determine the amplitude of Q. Okay, so we chose up as positive. So we know for a fact that if we're saying pulse P plus pulse Q should give us pulse X, isn't it? Yes. I'm just trying to write a formula. You can decide how you do this. So this implies pulse P, we got 3 centimeters. Since we chose up as positive, so it's going to be positive 3 plus, but Q is on the negative direction, so we're going to say minus Q is equal to, this one was also in the negative direction, so this is minus 5. Yeah, I think I'm gonna get sick of these bugs now. They just keep flying into my face. I don't know why. So let's keep moving. So how do we work this out? You know that you'll transpose Q to the other side. Q becomes positive. In fact, let's just be smart about it. When we transpose Q and rearrange, what will we get? It's going to be positive. It's going to be equal to, this is going to be 3. When you transpose 5 to the side of 3, it's going to be plus 5. So this is 8 centimeters. Of course, when you're not given a particular formula, try to work out one for yourself so that everything makes some sort of a mathematical sense. All right. So usually this is a 3-mark question. If you think about it, how many marks are we getting here? You're only getting 1 mark. Okay, so that is strange. By the way, it's fine. They know it's a very simple calculation. Let's move on. Now, Elena states that immediately after pulse P and Q meet, remember, immediately after they meet at point X, pulse P will move to the left. Is that true? Is that true? The answer is a definite no. They cannot. Remember, these are traveling in different directions. So at that point, they were just simply interfering with each other's with each other's paths. Okay. So they will just continue in their directions of motion. So that is not true. So what it says now, is the learner's observation correct? The answer is a definite no. So it is not correct. So 2.4. So I'm running out of space. 2.4.1. Why is this becoming like that now? So 2.4.1, we know that the answer is a no. Now 2.4.2, it says use a physics principle to explain the answer to question 2.4.1. Now once we are asked a question like this, it says you need a bit of knowledge from your textbook. So if you know these ones simply interfered with one another, essentially it means one was put on top of the other. That was a superimposition. So it is the principle of superimposition. Okay, of course you don't really have to state it here because they said use a particular, so by just identifying it you're getting your 2 marks. But you need to know, what does this principle state? Of course it talks about linear functions, so to speak. So it says in all linear systems, right, the response, or should we say the reaction to a particular phenomenon, right, is going to give us a resultant phenomenon. In fact, let me try to remember it again. It says for all linear systems, right, the response to 2 should we say disturbances, because we're talking about waves now, or pulses, it would be the reaction that we would get. What did I say? Yo. Okay, let's try again. It says now in all linear systems, right? Okay. The resultant reaction, okay, to 2 or more pulses or different pulses would be the sum of the individual pulses acting, alone. Do you understand what I mean? Yes. So these are simply just being superimposed, and they're just interfering, but they're not essentially stopping one another. One continues in its path and the other one continues in its path. So please, this is an NB. Just read about it and do a little bit of some research on your internet. Don't limit yourselves to your textbooks. Sometimes your textbooks are not the best in explaining concepts and at least bringing them home so that you can fully understand. So whenever the textbook doesn't seem to really make sense, go beyond the textbook. Go and find more examples. There are plenty more people on social networks who do some lessons. Sometimes they demonstrate how these work together, so you do not have an excuse for a stunted growth if you've been going to school. All right. Okay, all right. So that is the principle of superimposition of waves. Maybe let's just even state that we're applying this in waves. Move here. Because we're talking about waves. All right. Great stuff. Okay, guys, let's not relax too much. Let's move. We've got too many questions to deal with here. Now, question 3 says, the following wave pattern is produced by a wave that takes 2.5 seconds to complete one cycle. So that means the period is 2.5 seconds. That's what we are given. And the period is 2 successive points, is the time it takes, okay, from one particular point to the next successive one in phase, okay, with the previous. Okay, let's not even try to explain too much. Please know the definition of a period. It is basically it is the time taken to complete one full wave. Just understand that. Great. Now let's move on. So we can see here we've got this wave of ours here. It's going and going. How many waves do we have? It's 1. Sometimes it's nice to always explore what you've got. Okay, we've got another one here. I'm just going to use different colors just to play with it. And then we've got another full wave. And then here we've got half. This one is half a wave. So we can just use the period to assist ourselves here. We know that this is period 1, T2, T3. In fact, why do we even have subscripts? Maybe let's not put subscripts because it causes problems. We know that this is the period T, this is still the period T, this is still the period T, but here we've got half of T, okay, because it's not a full wave, it's half a wave. So please, guys, play with your diagrams. I promise you are going to understand the significance of this later on. Now it says a particle at point B vibrates at 90 degrees to the direction in which the wave is moving. Okay? Now, whenever the pulse is at right angles to the propagation or the direction of movement of a wave, this already tells us that we're dealing with a transverse, right, wave. Okay? Because with longitudinal waves, the pulse is in the same direction as the propagation of the wave. But when it is at right angles, the key here is that the pulse is at right angles with the direction of a wave. All right. Now, what type of wave is indicated in the diagram? Oh my goodness, 3.1. This is a transverse wave. Okay, we're dealing with a transverse wave. Okay. 3.2 says, give what reason why a particle at B is out of phase with a particle at C. Well, they're out of phase because they are moving in opposite directions. Okay, they are moving in opposite directions, so that is why they are out of phase. Now it says determine the frequency of this wave. Okay, so we want the frequency. So we've been given the period, so it's a 3-mark question, so it's a standard 3-mark question. So 3.3, we know that frequency is inversely proportional to the period. So basically we use that equation. It's there in your formula sheets. So this is 1 over, this was 2,5. So let's see. That has to be in seconds, right? 1 divided by 2,5. This is basically 0,4. Now what is the unit of measurement for frequency? Is hertz, which simply means per second. The guy who described this is some guy called Hertz. I don't remember his first name. Anyway, let's move on. So you get a mark for a formula, you get a mark for a substitution, and an answer. And your answer must have a unit of measurement, or else chisampama. You lose marks. Okay. 3.4. What is the story? If the speed of the wave is 0,8 meters per second, calculate the value of x. Okay, in meters. So now let's see. X is the distance between, you see we have sort of like a full wavelength here and a half of a wavelength, right? And then half of a half here. So basically here we've got a half of a half. And then here we've got half of a wavelength. Okay? And then here we've got 2 halves basically. So this distance right here is going to be a quarter of a wavelength if you think about it. And then here we've got a full wavelength. So basically to calculate this distance we need to consider these dudes. We need to consider this dude, that dude, and this dude right here. So the key is knowing the wavelength. And then we simply just do that calculation. Pretty easy. Okay, let's move on and do it. So here we know that the speed, the general wave equation, tells us that wait a minute, that the frequency is multiplied by the wavelength, and we know that for us to get that distance we need to find the wavelength. So this implies the velocity is 0,08 equal to the frequency. We calculated it above is 0,4. So if it is wrong, then you're dead. Okay, and then we want the lambda. Therefore our lambda is going to be 0,08 divide by 0.4, which is going to be 0.08 divided by 0.4. It's basically 0.2 meters, right? The wavelength is in meters. Okay, so this implies that x is basically is going to be equal to a full wavelength, as we could see there, which is 0.2, plus a half of a wavelength, which is 0.2 times 0.5, okay, plus a quarter, which is 0.25. Okay, maybe let's do it this way, 0.2 into 0.25, that's a quarter, right? So I'm just changing a half into a decimal and a quarter into a decimal, okay? Let's find out what is that. So 0.2 plus 0.2 into 0.5 plus 0.2 to 0.25. So I'm getting a 0.35 meters. All right. Great stuff. So remember this distance right here that we use as t. If we're talking about time, it is the period. If we're talking about distance, it's a wavelength, okay? Remember that. But we almost always use t for that particular situation. But when we talk wavelength, we can use that as well, but in terms of distance. So you can see that's why it's 4 marks, because it already tells you this is one of those questions that demand 2 steps than just 1. So of course here you won't really get a mark for the formula at this point. I'm trying to figure out where would you get the marks. I think this is the first 2 marks, and then here you can decide whether you're going to say correct substitution. For me, correct substitution into a correct formula is much more interesting than the intermediate answer. The formula, not necessarily something that gives you a mark. But if you mess up with your substitution, one may look into giving you a mark for your formula. I mean, you don't really have to lose marks here altogether. Anyway, that's how you answer that question. Now the question says, how long in seconds does it take for a particle to move from point A to point D? So how many periods do we have here? We've got this period right here, this same period right here, the same period right there, and then we've got half of the period. So basically we need to add those together. So we've already been told what the period is here. So we can just say T to answer this question. 3.5. We can say it takes 2.5. By the way, these are 3. There's 3 of them. Right? So there's 3 full periods. 1, 2, 3, plus just a half of 1. Half is 0.5. I don't know why my writing is trying to mess with me, which is equal to 2.5 into 3 plus 2.5 into 0.5. So basically I'm getting an 8.75 seconds. All right, so we've answered those questions nice and easy. Okay, again here you should be scoring around 2 marks. So first of all, for this left hand side and the final answer. Great. Let us move on. Question 4 says, a wave source on a ship sends out waves of frequency 2.5 kilohertz. Okay, to the bottom of the sea. The receiver attached to the ship detects these waves a short while later. Meaning, if we've got this ship sitting right here, okay, let's just say this is the surface of the water, and we've got this ship over here. So we've got the ship here, and then it's going to send a sound wave. Bong, 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 bong. Remember, the sound wave is a longitudinal wave, okay? It goes, and by the way, what is the story here? To the bottom of the sea, okay? Let's just say this is the bottom of the sea. Okay, it's not always that straight anyway. So it will hit the bottom, and then once they hit a particular surface that they cannot penetrate, what happens to the sound waves? They kind of propagate backward. So this is what we call reflection to a detector. If we say the detector is here, so that's the detector right there. Okay, so of course they said this is attached to the bottom of the ship, so this is not quite a good representation. So let's just say the detector is here. So basically it's going to send these sound waves down, and then they hit the bottom, and then they get reflected. So always remember, there's a certain rule that you're going to learn in grade 11 or so, but I think in grade 10 already you learn about it, the reflection. So the angle of incidence is the same as the angle of reflection of a wave. Anyhow, let's just leave that for a change and not go into too much detail. Okay, so this is what is going to happen here. Now let's go on and answer some questions. So when you're not provided a diagram, please try to draw your own so that you can make sense of the situation. So basically, if we're told that it took some 10 seconds, or it says a while later, it doesn't tell us how many seconds it took. So I've already looked here. That's the thing. That's the thing. You see, when you have eyes that are all over the show. If you saw on my video, there's a video I messed around on my piano. You'll see my eyes are all over the show. I'm like a thief, you know, trying to look for a spot and a position or an opportunity to steal. So you see my eyes always skimmed and scanned this whole thing. Anyway, so let's forget about the last question. Let's just answer them systematically. So it says now, the speed of sound in water is 1,500 meters per second. Okay, they are giving us this one. It may not be exactly true, okay, but this is what you're being given. So don't worry about what you know. If you are given something, you use what you are given. If no one mentions this, then you use the standard, okay? Now 4.1 says, what is an echo? Okay, which is how we apply this in the medical field and many other fields. So an echo is basically a reflected sound wave, isn't it? It is a reflected sound wave. Okay, is there anything? Yeah, man, if it gets reflected, it forms an echo, but we're talking about a sound wave, nothing else. Okay, but yeah, let's not even complicate this situation. So basically, an echo is what is produced by a reflected sound wave. So when sound is sent away, like in the case, it hits here, and then when it gets reflected back, what now this detector will hear is an echo of the sound that it sent away. Right. So if you go and stand somewhere near the caves or something, when you shout out loud, at some point you'll hear your very own self saying this a while later. This is when your sound is being reflected back to you from those caves, okay? Or any structure that will not allow sound to penetrate it. Okay. Easy stuff. Let's just leave it at that. We don't really want to say too much. Of course, please guys, whenever you are asked a definition, I make it my mission to suggest that go and read what that is properly so that you can have a proper definition. At times, yeah, these questions are way too far out of reach for me to say the exact thing, but I'll give you an idea at times. So this is mainly an idea. It may not be a true definition, but do double check with the memorandums or your textbooks or any guidelines that you've got your hands on. Now 4.2 says calculate the wavelength. So we want lambda. So we know that our general wave equation says V equals frequency multiplied by wavelength. Okay, so which will imply that now we were told this is 1500 equals the frequency we're told is 25 kilohertz. Now kilo is times 10 to the 3 times our lambda. Therefore, our lambda, which is the wavelength, is going to be equal to 1500 divided by 25 times 10 to the exponent 3. So easy stuff here. So 1500 divided by 25 times 10 to the exponent 3. So what I'm getting here is 0.06 meters. Remember, this is in meters. Okay, that's great. So here, standard 3 marks. You get a mark for the equation, you get a mark for a correct substitution, you get a mark for an answer. And don't forget, there must be a unit. Okay, all right, okay. Next question says, can these sound waves be heard by a human ear? Now, if any one of you who wrote this paper watched my physics paper from October last year from the Eastern Cape, there was a mention of what a human ear could hear. All right, so technically, if you pay attention to some of the information you come across, it becomes an advantage for your next opportunity. All right, remember, there's no such a thing called luck. A friend of mine told me that luck is essentially when what is the story? It's when preparedness comes in contact with opportunity. Is it? Yeah, he said something like that. So when you are prepared and your opportunity comes, that's what it's like. But if you're not prepared, believe me, any opportunity can be a waste of time, or at least be missed, or to have no effect in changing your life. So remember, you're not just going to be lucky if you're not prepared. You must be prepared for an opportunity that comes when you least expect it, to matter in your life and for you to take full advantage of it. So please, guys, have a tendency to not just go through things for the sake of going through things. Go through things and learn from each and every exercise you partake in. And don't just sit there and watch a video from the beginning to the end and that's it. be actively involved. If you hear someone mention something, write it down on your whatever notebook or whatever page. Make sure you go back and read about that particular phenomenon to expand your knowledge on it, so that it does not become a problem for you in the future. Okay. Anyway, I was just saying something about this because that question paper mentioned and even stated exactly what is that value. So you may know, you may not know, but if you watched my previous video, you are at an advantage for 4.3. So the answer to 4.3 is so. Is this sound possible for it to be heard by a human ear? The answer is no. Okay, it said give a reason. The reason is that we know that the sound frequency given, right, is outside the range that a human ear can detect. Okay, let's write English properly. Something is starting to irritate me. It's outside the range that a human ear can detect. What is that range? We know that a human ear can hear anything from 20 hertz to 20 kilohertz. Okay, especially babies. But an adult, it can drop to around 15 to 17. Okay, but we'll assume we're talking about a healthy individual, young adult or something. But an older individual, like an adult person, it's around 15 to 20. So meaning 15 hertz to like 15 to like 17 kilohertz. So, but technically, the range that is given in most texts, I don't know if your books mention this, but this might be something you want to put into your memory. As you can see, you are asked something that is not provided in your information sheet. I am a bit sure of it. Let's just go and have a look if it is there, just for fun. Guys, we've got plenty of questions, so yeah, doch. There's bugs, man. See, it's not there. So you've got to know. So if you watched my video, you must have been smiling. But if you watched it carelessly so, you will be like, yo, I wish I remembered. Because trust me, a single mark is so important. You will not believe what it can do for you. It is the difference between scoring a distinction or 100% or a fail, okay? So there you go. You're getting your 2 marks. Next question. Hi man, don't use it. Next question says, calculate the depth of the water beneath the ship if the waves are detected by the receiver 10 seconds after being emitted. Again, this is a question that is related to one I did in that paper. So if you did pay attention, you definitely got this 4 marks in the bag. Okay, so let's start 4.4. Now remember, we want the depth of the water. So exactly what is this distance here that was traveled? Okay, again, distance, we know that it is the speed. So we know that in general, speed is basically distance over time traveled. Okay, now we know here that the speed here is 0.5. okay, 1500 meters per second, equal to the distance. We're just going to keep it to d, which is now the depth of our water. But now here's the problem, the time it takes. Remember, we're going to be using time symmetry here. So it says to us, this whole business here, got you, this time business here, it means the time it takes to go down is the same as the time it takes to go up. And we know that the total time is going to be 10 seconds. But now we're only interested in the travel from here to the bottom. So this means for that phase, it's going to be half of 10. Okay? So I'm sure you saw my calculation. Even though there was a bit of a mistake on the Eastern Cape's memorandum for that question, I kind of corrected it. So I do believe and hope you got it right. Okay? Unless your textbooks or your teachers or exam guidelines are saying otherwise. But a friend of mine who commented, they kind of confirmed the fact that the suggested approach in that video by me was correct. Okay, so I believe this should be correct as well, but do double check the memorandum as well to make sure you're doing the right thing. So now the time here is going to be half of 10, because we're talking about just going to the depth. So the depth is just the time traveled, which is half of the time it traveled to and back, isn't it? So that's just the key here. And then of course this is over 1, so you know you cross multiply here. So what can we say? Therefore d is going to be equal to 0.5 into 10 multiplied by 1500. So that will give us the depth in meters. So 0.5 into 10 into 1500. So it gives us 7,500 meters deep. Okay. So that is the story. That is the depth of our sea. Now again, it's a standard 3-mark question, so to speak, because you get a mark for a formula, correct substitution, but this calculation on its own is a critical step, I believe, so you should be getting a mark over there. The gymnastic is really great. What? You do this kind of a thing in grade 9 or grade 8, somewhere there. So the final answer, remember, the final answer must contain a unit of measurement. If it is missing, you are dead meat and we eat it. Okay, let's move on. Question 5 says the electromagnetic spectrum includes, amongst others, radio waves, ultraviolet waves, gamma rays, visible light, and X-rays. So this is basically a very haphazard way of, putting these. They were just put in like a mixed masala. Anyway, so we know that the organization, if we list them from, the lowest energy to the highest, the lowest energy is going to be the radio waves. Okay? And then we go on to the next one. It's going to be a microwave, right? Which is not included here. And then from a microwave, we talk about infrared. Okay? Infrared, I don't know, is it infrared rays? Something like that. And then we talk about visible light spectrum. And then we're talking about UV rays, ultraviolet. From ultraviolet, we get X-rays, which we use in the hospital to image our bodies so that we can find out if we've got a broken bone or some organ that looks bigger than the others or some abnormal patterns. Anyway, from there we're going to gamma rays. Okay, which is much more dangerous than the rest. Okay. So you can already tell here from visible light backward, everything is a little bit okay. But from here onward, this can be very dangerous. This group here is the dangerous group because it can cause DNA damage to cells. And once there's damage to the DNA, it actually fragments. And once DNA fragments, sometimes it depends on whether that fragmentation is one which cells can repair within reasonable time before that DNA starts to form, very bad combinations and starting into a secretion of bad proteins that cannot be controlled, and the cells divide endlessly, meaning forming some sort of a cancer. Okay, but the others, they don't cause that much damage at all. Anyway, let us look at what is the story then. Briefly explain what is meant by dual nature of electromagnetic radiation. Well, we know that we found out from our masters of the past that the dual nature basically means EM has both a wave nature, meaning, what do we know about waves? Waves can travel through a medium, waves can be reflected, waves can be refracted, there may be some interference patterns. So that is what we mean by wave nature. We're talking about all of those properties of a wave: reflection, refraction, interference, travel through some sort of a medium at different speeds depending on the medium, all of those things. It has frequency, amplitude, wavelength, all of those things. That's what we mean by the wave nature and a particle nature. Basically, if light is a particle, we consider it as some packet of light, like photon or packet of energy. So it can deliver all of that to any electron it can come in contact with, So those are some of the things. This is coming from quantum mechanics, okay, or quantum physics. Anyhow, all you needed to know is the wave nature, meaning it has all the properties of a wave. Those interference patterns, refraction, reflection, diffraction, refractions, you name them, depending on the type of wave, of course. But we know that this particular type of wave is technically the so-called transverse form of waves, because these are high energy type of waves. So they kind of move particles more in the transverse section to their pulses than it would be the case for sound waves. Anyhow, we are where we want it to be. So basically getting a mark for the wave nature and the particle nature. Now name the type of electromagnetic radiation that. So 5.2. So we've got 5.2.1. It says now name the type of electromagnetic radiation that is used to sterilize medical instruments. Okay. Whoop. I knew there was going to be trouble. So I don't know, guys, maybe it's iwena masenhlanyela kanti 10 gogland kini number 14. Okay, so what do we use to sterilize? Okay, those of you who are going to join the medical field, you will realize, or you will come to learn, that the reason for sterilization by using okay, let's not yeah, it's actually ultraviolet. Okay, we use ultraviolet. Now I don't know why I wanted to use that. So we use UV light, so it's ultraviolet. Ultraviolet rays. That's what is used for sterilization of medical instruments. Okay, now I'm a surgeon. Okay, so I use a lot of these things, and I get mad when some of our machines that deliver this type of rays are not working. As you know, our government doesn't want to pay money to fix these things or to maintain them or to replace them when they are messed up. Whenever money is returned to the province or to national, they split it for themselves instead of keeping it, so that whenever there's a need, something is broken somewhere, they can actually mobilize that money to that effect. Anyway, talking nonsense. The reason for using this, we know that bacteria, like viruses and bacteria, it depends on what forms of bacteria. Sometimes they are so-called diplococci. Coccus means circular, right? And then we may have something like this, like a rod. When it is like a rod, we call it it's a bacillus. You will know that in biology, when something is rod-shaped, it's a bacillus. I'm just giving you extra information now, which you don't need, but you know what? We call it bacilli or bacilli. And then if it is sort of like this, it's coccoid. It means it is circular. Okay, so if it is circular, I don't know why I'm writing circular. This is what we call a coccus. Cocci. They call it cocci or cocci. All right, not a problem. So when there's two cocci or coccis, we call it a diplococcus. This is a bug that you would call Neisseria meningitidis, which causes meningitis in children mostly. And this thing can kill, okay? It's dangerous. And then I think syphilis. Is it syphilis? Yeah. But syphilis is caused by spirochete, is it not? I'm trying to think, man. Is it gonorrhea? Yeah, I think it's gonorrhea. It's a diplococcus as well. Anyway, sometimes I forget these things. I know how to treat them. So that is the story. So basically, yeah, I'm giving a little bit of some nomenclature in biology. You will read this one in the so-called taxonomy and systematics when you're doing university stuff, and then you're doing things like botany or whatever. But when you're doing medicine, you will definitely learn about so-called taxonomy and systematics. You name these bacilli or bacteria according to their families and species. That's why they've got two names. The family name is the first one, and then the species name is the last one. Okay, anyhow, let's just move on. So these things, we are inflicting DNA damage. That was where I was going with UV light. Okay, and this damage is so great that these bugs are not able to repair it, and therefore they die. That means when we use these instruments on any individual, we will not be planting any of these bugs that were initially there, because they are in the environment, remember. So we open these and use them immediately in a surgical environment and quickly finish, because the longer the procedure takes, the more bugs will actually start attaching themselves on those instruments and eventually give someone an infection of that wound that we worked on. So this is why certain people will get some infections post-operation, and most likely long procedures result into some sort of an infection of the wound. But short procedures, because we use these while they are still sterile, meaning no bugs that are alive are on those instruments. And if the procedure is quick, then you will see that most of those people do not acquire any infections. But there are many reasons for infections to occur during surgery or after surgery. But in any case, let's just move on. So the key here of using this to sterilize is to inflict DNA damage. As I told you, that from UV to gamma rays, these ones cause so great a DNA damage that almost always, if you're exposed to these, you get cancer. But yeah, well, UV and X-rays are not that bad, but they are bad, okay? They are bad. We've seen a lot of people who use these, especially surgeons who work on the spine and orthopedic surgeons. They use X-rays to kind of know exactly where they are and exactly whether the job they're doing is, doing the things that must be done or not. So I unfortunately am one of those who use X-rays when we're doing work on the spine or we're doing work on the brain, trying to locate a blood vessel. We use fluoroscopy, which is, of course, some modifications of X-rays, less energy or less, amount of photons there, so that whatever damage or exposure we get, it's not as damaging as it would be if we're using gamma rays. Gamma rays are a dangerous one. So we use these ones for treatment, basically. You will see some word written RX. This is for treatment purposes. When you're treating cancers, you use anything from, you can still use these ones, because remember, radiotherapy is what actually uses X-rays, but more of these X-rays than it is for just regular X-ray films that we use to just image your chest, your bones and stuff. But when you're doing radiotherapy, you're basically using any of this. There's something we call a gamma knife. It uses gamma rays to destroy cancers. Because of the speeds of travel and the deep penetration to tissues, you can use these ones for deeper lying tumors, where you need to deliver the highest form of energy to damage those tissues. But of course, you will learn and you will learn and you will learn and you will learn. I'm just giving you a heads up that studying these things is not a waste of time. Some people keep asking, when will you use these bits and pieces of information? If you don't already understand them now, it makes no sense when you get to their applications, especially in the medical field. So you become a bit of a dangerous person because you're using what you don't understand. And that means when it is doing wrong things, you won't even pick it up unless someone else says so. And that's not what we want to produce. We want to produce people who are rational and are very good at thinking, and because they have a deep understanding of materials, which is what we call insight. Anyway, guys, I was not giving a medical lecture or some biological lesson whatsoever, but I'm just trying to show you where physics applies in some biological mechanisms that are of importance in our daily lives, or should we just say in our living. Anyway, so we said it's ultraviolet rays, okay, because as bad as they can be, they are not enough to really cause that much damage. Yes, they can cause some skin cancers and stuff like melanomas and whatever, basal cell carcinomas, squamous cell carcinomas and all. But it's not so common if we control how much exposure we have and allow time for, the cells to repair themselves, which is also one of the things that explains the importance of radiotherapy to be spaced apart. You can't just get radiation today, tomorrow, the other day, and that day. You get one today and then you go home, you let the cells recover and all that. Normal cells will almost always recover. Some of them that are getting a lot of exposure to this, they may die. Hence we see some side effects or complications of radiation therapy, which is an untoward damage that happens. And we call it iatrogenic damage because, we cannot avoid it. It's like when there's a war, when there's like explosions and stuff, a lot of innocent people get caught in the mix. And what can you do about it? Are you going to say, let's not fight wars when we need to, just because some people are not going to live? Well, if they are less than the numbers that will survive the war, then so be it. So this is the same concept with radiation therapy, where you're going to inflict so great a DNA damage to cancer cells because already having abnormal divisions, they have abnormal biological mechanisms that govern their growth and multiplication. So if you damage them so much, they tend to, the tumor tends to regress and actually ends up being finished. But at times, certain tumors are just bad. If you expose them to radiation, they actually become worse, okay? We unfortunately have had a case like that. So unfortunately, the results didn't come right. But let's go on. Okay. Now, which one of these electromagnetic radiations has the longest wavelength? Remember, the length of the wavelength is inversely proportional to frequency, as you can see from the general wave equation. So if we're talking wavelength, it is going to be V over frequency or vice versa. So you can see that these ones are inversely proportional. So we know that lambda is inversely proportional to frequency as a result. Okay, so what does that mean? Something that has the longest wavelength, it has the lowest frequency, meaning the less energy. So this is the least that we study at school, okay? We study this one, the radio waves. So remember, they just mentioned, you're not going to answer according to this. This was just the standard stuff. I was giving you information, but of what we were given radio waves, ultraviolet, gamma rays, and visible light, and X-rays. So they kind of left out the microwave, the infrared. Sorry, yeah, that's it. So here, of what we were given, the radio waves are the ones with the longest wavelength because they are of the lowest frequency, and that means the lowest of the energies. So 5.2.2, it is the radio waves. Okay, not a problem. So now you would be told time up, okay? I kind of indulged, guys, so I had to give you a bit of why you need to study these with care and make sure you understand. This is an NB for someone who wants to become a doctor of any kind, because these are heavily applied in medicine. Of course, even others, because they explain why these things work the way they work. So you need to understand the whole subject. Let's move on. Now, it says state one danger of ultraviolet light. As I already stated, as much as we use it for, sorting out our problems, it can actually create problems for us. It can cause cancer. So 5.3, it can cause severe DNA damage to cells, leading to cancer, okay, or development of cancer. Let me write properly. I don't know why, I always rush everything. This can cause severe DNA damage to cells, leading to cancer development. But you heard what I said. So I'm just saying a lot. You can just say development of cancer, basically. It's as simple as that. Now it says 5.4. We are told here, a photon of an electromagnetic wave has a wavelength of 700 nanometers. Okay, now calculate the energy associated with this photon. Okay, let's see. We know that energy of any photon is Planck's constant multiplied by the frequency of that photon. Okay, so we go on and say, fine, Planck's constant stays, but what is frequency? we are given a wavelength here. So from the general wave equation, V equals, but remember now when we're talking about rays, we use C instead. C is frequency multiplied by wavelength. It's the same thing, general wave equation, but we use C because C is a constant. Okay, we know that this is a constant and its value is 3,0 times 10 to the exponent 8 meters per second. Is it? Yeah, I think so. But again, if you forget that constant, we come here and check it out. It is, yes, 3 times 10 to the times 10 to the 8 meters per second. Okay, so from this general equation, we can see that, well, if we have wavelength, we can actually determine frequency by substituting here and say, look, if we work out frequency here, frequency is going to be C over lambda, right? Yes, so that is the story. So now we know we can say this is going to be C over lambda. That is frequency right there. So frequency is being replaced by that expression from that general wave equation, but in terms of light this time around. Planck's constant is 6,63 times 10 to the minus 34. Now we're going to multiply this. Now what is that? This is 3,0 times 10 to the 8 divide by, now this wavelength is 700. Nano means times 10 to the minus 9. Okay, again, remember these prefixes, we call them prefixes, and know them all. There is a table in your textbooks that lists all of these things, so you should be able to do it. Okay, let's do the calculation. You can do this in 2 stages, but I am not really a fan of less integration. I prefer to integrate more than I do not, because I feel you guys are being, you're being made into the best, so you might as well be expected to function like the best. Because if we give you too much soft milk, banikindengane or nestam nizothamba nibe weak. As professionals claim degrees and what. So there's a week ungekho umfanise ne-degree akanayo or whatever qualification. We want someone who's at degree. Remember, energy is in joules. Xa ifika umuntu esithi ndine-degree, funeka ungamphazami kwa indlela kathetha ngayo uhle uyive nje uba ndithetha nomuntu ofundile, hayi nje qaba. Khonto wrong uba liqaba ke kodwa, because you choose uba liqaba kwezi ntsuku. Back in the days, it was not really a choice. It was more of, a situation. Gogo, it's up to you if you become, a hooligan. In fact, I'll call it a hooligan, even though Balikaba doesn't mean Windlavin. But Windlavin if we get Balikaba go. And it injalo lento, ijwalo ntweni. Wabona? Ulukile hair. It's alright. Now, how many marks do you get? You get a mark for this. Now you get a mark for the general substitution, but this calculation is a special one. It could have been a different step altogether, and then the final answer. As always, your answer must have units, okay? So guys, we are doing fine, okay? That's how you get those marks. And by the way, there's another thing here. Knowing this part is also an extra mark, okay? Knowing the denominator that you're going to express it like that is an extra mark. So you're getting how many marks? 1, 2, 3, 4, 5. So that's how you're getting those 5 marks. It looks like it's a lot, but it's not. So you need to know how to convert that or to write it out. Okay guys, not a big deal. Let's move on. Now it says, how will the energy of this photon be affected if its wavelength decreased? So remember, shorter wavelength, it means more frequency. More frequency means more energy. So it basically increases. Okay? And what is the story? Give a reason for your answer. So now 5.5, we know that it increases. Okay? The reason we know that energy is inversely proportional to wavelength, isn't it? Yeah. Sometimes you can use an equation. Remember, there was an etc. there. You can write it like this. That's a reason on its own. They didn't say in words, okay? Or you can write it out and say energy since energy of a photon is inversely proportional to the wavelength. You could see that. Of course, you read it from this very equation right here. You can see the wavelength is on the denominator while the energy is on the numerator. So that's an inverse proportionality. Okay? All right. So you can write it as a formula. No one is going to punish you. They said etc. Or you can write it in words. If they say give a reason in words, then you are only stuck to the words. But if they didn't say, you can just write that. And that is great. So you get your final 2 marks. All right, guys. Yeah, this is nice. Okay, let's do... Oops, okay, I'm going to try and move quickly here. Now, two identical insulated. What is the significance of them being insulated? Is to create a closed system. Okay? Right. Remember, total charge in an insulated system. So, total charge in an isolated system, or isolated, you can say closed system, is constant. All right? This comes from the so-called charge can neither be created nor destroyed, but can be transferred from material to another, right, in a particular system. So that is the story there. So to put it nicely scientifically, we can say the total charge in an isolated system is constant. So by insulating these, we're making sure that they don't interact with any other materials in the environment, but only within this created system of ours here. So please understand certain inferences in science. Okay, they are held together a small distance apart as shown in the diagram. Of course, if you are doing grade 12, you would know you're doing Coulomb's law, but in grade 10, nah, you don't do that. You don't do that, or at least I'm not sure, but I don't think so. Now let's move on. So we can see this is plus, so it's a positive charge. It's a positive charge, so it's a plus 6. Hi man, so it's a plus 6 times 10 to the minus 18 coulombs. And then this one is unknown, but all we know is that it's a negative charge. Okay. Now sphere X carries a charge of 6.4 times 10 to the minus 18 coulombs, while sphere Y has an excess. Oh, doch, that is good. It has an excess of 30 electrons. So meaning the charge here is minus 30 into 1,6 times 10 to the minus 19 coulombs. All right. We can actually work that out. So this is 30 into minus 1,6 times 10 to the minus 19. So this gives us a minus 4,8 times 10 to the minus 18 coulombs of charge. Okay, that's great. So that's what we're getting. So they are indirectly giving us the charge, meaning you have to work it out. So be comfortable using given information to work out things as you need to. So I promise you guys, if you adopt the attitude and the ability to interpret information and be comfortable working things out before anyone asks you a question, at the same time, you make sure that you understand the information provided. It makes life so easy when you're answering questions. As you can see, I indulged here, but I'm not too far off the time that I'm supposed to be doing. Okay, the first question says, calculate the magnitude of the charge on sphere Y. We just did it, so that's fine. So 6.1, we can say Y is going to be 30 into minus 1,6 times 10 to the minus 19 coulombs. But of course, when you substitute, you don't really have to write it down. And you saw this is minus 4,8 times 10 to the minus 18 coulombs of charge. Maybe we can write it like that. Maybe let's write it properly. So the charge on Y, okay, is like that. Great. 6.2 says, the spheres are allowed to touch. This question is common. If you watched my video, the previous one from the EC, it's more or less the same thing. So you must have seen that it's just taking marks away. After touching, they move away from each other. Now it says, state the principle of conservation of charge. Okay. Now it says, charge cannot be created nor destroyed, but can be transferred from one point to another, or from one material to another, if they form a particular system, so it doesn't get lost. All right, not a problem. So now to put it nicely, we can just say the total charge in an isolated, sometimes you can use the word closed, doch, is constant. Okay, so that is the story. This explains that charge cannot be created or destroyed, but can be transferred, just like energy, because charge is not so different from energy, is it not? Yes. Anyway, let's move on. This was 6.2.1. So we are in trouble a little bit, so let's move it. Okay guys, I'm trying to follow the rules, so I'm not going to give you poison. So this was 6.2. Okay, these are the sub questions of a sub question, so these ones we can make them follow each other. 6.2.2, it says, give a reason why the spheres move away. They are repelling each other from each other after touching. We can just say they repel. They repel each other since they since they will have the same amount of charge after they touched. Okay, of course try to answer fully, but you can do telegraphic sort of answers, you're still okay. So what's the story here? Calculate the charge on each sphere after they separated. Again, this is a good question, easy marks here. You've been shown already, so we can say that the new charge on each sphere How do I write sphere? Is equal to, it's going to be qx plus qy divided by 2. So this was plus 6, 6,4 times 10 to the 18 plus this is now minus 4,8 times 10 to the minus 18. I don't know what I'm doing there. That divide by 2. Okay, so let's do it. So this is 6,4 times 10 to the minus 18 minus 4,8 times 10 to the minus 18, then divide by 2. So we're getting a plus 8,00 times 10 to the minus 19 coulombs. Okay, or you can just simply write 8, just write 8 times 10 to the minus 19 coulombs. Okay, so that's the story. So here it's a simple procedure, some sort of a formula. It doesn't have to be a standard formula. Substitution and answer. And don't forget, for the answer there must be units. Easy 3 marks. Let's move on. 6.3 says a neutral sphere Z. Okay, if it is neutral, what do we know? The number of electrons is equal to the number of protons. Yeah. Great. So these guys, however many they are, sonhlanyela wena, skantina wena. So it's going to be equal to the number of the protons. So here we know that Ne is equal to N. Protons, what can we write? Let's just write positive charge. Okay. So that is the story about our sphere Z. Okay. Now is placed next to sphere Y as shown below. Now what is meant by the neutral sphere? Okay, it means the number of electrons equals the number of protons. So 6.3. So we can say now, okay, let's write properly the number of electrons is equal to the number of protons. Or if you like, you can say the number of negative charges is equal to the number of positive charges. But by definition, electrons are negative charges, protons are positive charges. And if it is neutral, that is balanced. Great. So 6.3.2. It says now use a sketch to show how the charges rearrange themselves inside sphere Z. Okay, so what do we know? We know that this is now a positive. And what is the magnitude is what we calculated above. So it is a plus 8 times 10 to the minus 19 coulombs. Now if this is positive, it will attract these electrons, right? Right. So it says, how will these rearrange? So basically, they will arrange such that we will have, if you think of Y here, Y is positively charged, isn't it? And then now we know that Z here is basically neutral. So what will be happening here is that the negative charges are going to be more on this side. I don't know how you're going to show that. Whereas the positive charges will sort of like remain. Okay, maybe let's do a better structure. Remember, these ones were evenly distributed all around the sphere. Maybe let's just show it nice and easy. So this is an electron, this is an electron, this is an electron. So do you see they're evenly distributed? So when now this happens, we know that these electrons will try to be attracted by that charge, because this one has a much bigger positive charge than probably this one is. It doesn't really matter. I don't know how you're going to show that you have a positive charge in the center, but this diagram is not doing it. Let's make it bigger. So we've got we've got Y here, which is positively charged. Basically there are no electrons here, it lost them all. And okay, not all, but it lost many. And then here we've got Z here. So the negative charges are going to be arranged on this end, whereas the positive charges will be on the other end, because they're being repelled by that. So the positive charges will be somewhere on the other end. I don't know, guys. Check the memorandum or check your books. I'm not really familiar with how you actually would draw your diagram. Yeah, doch. It doesn't matter. So I don't know how you're going to show it, but for just 2 marks, I think that what matters is to know that these ones will rearrange so that they face these ones, because there is an electrostatic force. This charge is going to try and pull these electrons from that one. So it will be trying to pull these electrons towards itself, basically, while it's repelling the positive charges away. Okay, so we know that the force to these positive charges is away. Something like that. I don't know how you're going to draw the diagram. You double check. Okay, move on. Last question. Okay, guys, let us do it. Now, study the circuit diagram below. Ignore the resistance of the battery. So if we are told ignore the resistance of the battery, it is somehow said to be negligible, meaning it's too small. It's too small to have any effect in the circuit. Okay, so meaning you can just forget about it. Basically, it does not lead to any energy dissipation whatsoever. So that means whatever the battery is supplying is exactly what we're getting. So we know that these the longer ones are the positive terminals of each cell. Okay, so this is one cell. So that unit is a cell. I don't know how this is going to be. So this is one cell, okay? All right. And then this unit, these are some of the things, guys, you want to play around. That's another cell, okay? And then this is another cell. So sometimes you can be asked a question as to how many cells make up this battery. You need to be able to tell that there are 3 cells. So basically this is a cell, okay? So in total, we've got 3 cells. All right, not a problem. Not a problem. So we've got 3 cells. This battery is made up of 3 cells. Now, what do we know? Conventional current is from the positive terminal, gets to this point, then the current will split because this is a parallel connection. And then here it comes together. Okay, and then the circuit is completed. Of course, we are being told here this battery does not get warm when it is in operation, but in reality it will get warm because we're going to be moving charge against a potential gradient, so to speak. Anyway, so that is what we've got. So this A2 is a portion of that, this is a portion of that. So basically it will depend on the ratios of these resistors to decide how much of this current passes through here and how much of the current passes through the second resistor. Great, so let's go on. It says define terminal potential difference. Okay, so basically this is the potential difference across the terminals of the battery when the current is passing through the circuit. That's what it is. This is what is supplied in the circuit. So 7.1, we know that the terminal and as Tensen Palakag begin. We know that the terminal potential difference is defined as the potential difference across the terminals of the battery that supplies the circuit. That supplies the current to the circuit. Okay, basically it means this is the potential difference across the terminals of the battery that supplies the current to the circuit, meaning the current should be flowing through the circuit for one to talk of a terminal potential difference. When there is no current passing through the circuit, we're talking of the EMF. Okay, great. Now let's go on 7.2. So please look out for definitions. I don't know how this thing got you. I don't know how many I've killed, but they just keep coming. I don't like insects. Anyway, so 7.2 says calculate the reading on the voltmeter V if the battery, what is it? The battery transfers 3 times 10 to exponent 4 joules of energy per unit charge. That is 2.5 times 10 to exponent 3 coulombs that flows through the circuit. So this is easy because by definition the potential difference is basically work done to move a unit charge across the circuit. So what is the story here? Easy. 3 times 10 to the 4 divide by 2.5 times 10 to the 3. Okay, so that is easy. So 3 times 10 to the 4 divided by 2.5 times 10 to the 3 is 12 volts. Wow, the same thing we calculated in the long questions. So in the MCQ. So do you see, I always said it, MCQs are most likely the topics you're going to come across in the long questions. So they kind of give you a preview. Sometimes they can be challenging, sometimes they can be easy. So how many marks was this? Easy, 3 marks. So formula, substitution, answer. And always make sure your answer has the unit of measurement of voltage. Okay, so determine the reading on ammeter A3, right? So we want this one. If the reading on ammeter A1 is 1,62 amperes and the reading on ammeter A2 is 0,65, so this is easy, very, very, very easy. So 7.3, sorry, it's a direct split. We know that A1 is basically equal to A2 plus A3. So A1 is given to us as 1,62 is equal to, we want A3, is that right? Right, so this is 8, this is 0,65. And then we know that our A3 is going to be basically 1,62 minus 0,65, which is basically 0,97 amperes. So it's a very simple calculation, but I'm giving a bit of, the things. But here you're only getting this mark for substitution in the answer, because this is not necessarily a recognizable formula. You just made it up for yourself. But if the marks were more, probably you would get an extra mark. Anyway, let's move on. Now it says, how will the resistance of R1 compare to the resistance of R2? Choose from greater than, less than. Remember, the greater the resistance, the lesser is the current passing through. So now let's see which one is greater. A2 is 0,65. 0,65 is less than 0,97. So it means more current is passing through R2. Therefore, it means it is of a lesser resistance than R1. So what is the question again? How will the resistance of R1 compare to that of R2? So R1 is greater than R2. Okay. So 7.4. Wow, I ran out of space. Okay. Is greater than, because if it allows less current to pass, it must be greater than that which allows more current to pass. Okay, so switch S is now opened. So once we open switch S here, like that, it means we are breaking this circuit. Okay, once we break the circuit, guess what? This will read what we call the EMF, because now there's no current that is going to pass through the circuit, because it's broken, it's incomplete. Current only flows when the circuit is complete. So let's see, okay, what term is used to describe the reading on the voltmeter? It's going to be the EMF, because that is the total voltage supplied by the battery when no current is passing through the circuit. So 7.5, we call it the EMF. I don't know. Sometimes it's safer to write this one. We can say electromotive force. I don't know if you break that word or you write it as a single word. Sometimes, things escape the guy. So the guy sometimes is able to create some controversial statements. Okay, guys, that's the end of our video. At least I took 2 hours, which I planned to take anyway. But you can see here, if I did not indulge, I could have explained quite enough for you to understand each section and gotten to finishing this paper still within the time provided by the paper. So this simply means when you're writing for yourself, you will be definitely able to write this paper from start to finish while making sure you're taking a bit of time to make an understanding of every scenario given to you and to ensure that you're doing a great job. Okay, guys, I hope you enjoyed the video and that you will consider yourself subscribed into this channel, because there will be more work for grade 10s that I'm going to do, and I will also slip in some work for grade 11s as well, so that at least this year we can have a bit of a balance. I've been doing metric entirely, should I say solely metric material in the past 2 years. Strange, right? Yeah, it's strange. It's been 2 years, but it doesn't even show. Anyway, time flies. So I hope you guys are going to make sure you go back to your books and revise these topics. Make sure you don't move along without understanding these topics properly. So this is your best chance to review them, because most likely you're going to meet them when you're doing your finals, and they are going to hurt because there's a lot of confusing materials that are still to come and that are there for you to also understand. But I will see if I can find other papers from other provinces and do them, for the sake of just making sure these whole concepts sit nicely in your mind. I think grade 10 exams are fairly easy compared to grade 11 and 12. Those are a bit more challenging, especially grade 11. So yeah, we'll see. And then before you do your June exams, say next month, I'll probably do some more work now related to materials that are going to be necessary for your second term examinations. Again, please, I advise you to work with me, work through all the papers that I work for you, make sure you understand, and do others that I didn't do. You will see 100% is yours, or a very high mark for your June exams. Nonetheless, keep the faith, work hard, don't entertain rubbish, spend less time doing unnecessary things like watching people being silly on social networks, doing really stupid things, trying by all means to trend. Make sure you do get a bit of time to look at those things, just for the sake of, breaking, because you do need some time out as well, so that you don't override your brain, but spend more time using your brain. Trust me, it hardly gets tired, but the body gets overwhelmed, okay? It's only the body that gets tired, but the brain, it doesn't, because even when you sleep, you still experience dreams. That is your brain working. You still breathe. That is your brain working, okay? You still get a heartbeat. Well, the heart beats on its own, but it gets an enhancement and a modification of how it beats from the brain, okay? So your blood vessels maintain tone so that blood can flow through. That is still the brain working. Your muscles maintain a bit of tone. You lose it. You lose it slightly though, but it is not altogether lost. So that is your brain still working. So your brain doesn't get really so fried that it cannot function, but it just decreases the level of functioning when you're sleeping. All right, guys, goodbye. See you next time.